Good morning to all of you. I am Mr. Ish. Thank you for joining me for this video, exponential functions versus linear functions. We have a coordinate pair over here, 0, 20,000, 15, 400. The x-axis value here represents time in years. The y-axis value represents the value. This right here are indicating the price of a car, a brand new car, the first initial time you buy it, which is time 0 because no time has elapsed. And 15 years later, the value of that car has depreciated quite a bit to $400. You can easily develop this in terms of a linear function and equation because you have your coordinates, and you can do an exponential function. The exponential function is, in its very simplest form, something which looks like that, where y can be f of x. But in a more appropriate format, you have ae to the bx. You have a coefficient here of your exponential base, then you have a coefficient here which is for the exponent x. If you have a positive value over here, you're looking at something which looks like that. I'm not going here in the negative x-axis values because time cannot be negative. However, if you have a situation here where the exponent is negative, you can have something coming like this, a downward sloping exponential curve. It depends on how the equation formulates. You can either see this or you can see this. This means that something over time is increasing. This here indicates that with time something is decreasing exponentially, and this very well would be the case of something which looks like this, that it is initially worth more when you bought the car, but after a period of time the car has devalued quite a bit. So let's look over here and then see what we can do with these values. If you want to develop the linear equation, you know that's easy. Y equals mx plus b. You have to find the slope first. You'll have a 400 minus 20,000 divided by 15. This right here is y2 minus y1, x2 minus x1. And you can easily get the slope, and let's do it. We have 400 minus 20,000 divided by 15. We have here a minus 1306.66. And the equation here is easy because we have a y-intercept. Easy. We have a minus 1306.67x plus 20,000. That right there represents the linear equation, and we'll set it aside. And it could be a good one or it could be a bad one in terms of how accurately it depicts the value of a car over time, but that right there is the linear equation. Now we have to develop the exponential function, and we'll do that. Think about everything here with y equals ae to the bx, and looking here at the first set of values, you have a x value and a y value, and you plug them in. Your y value here is 20,000, you have a, you have e, you have b times 0. B times 0 is a 0. You're basically looking at just ae to the 0 is equal to 20,000, and then e to the 0 is 1, a is equal to 20,000, and you've gotten your coefficient a. And now you rewrite everything with your new information, which is your a value, and now you have to solve for the b value utilizing the next set of coordinates. You put the x and the y value where they fit. You'll have a 400 is equal to 20,000 e to the 15 b. Now you have to do basically the properties of logs. You'll do 400 divided by 20,000. You'll do a natural log of this, which will be a 15b natural log e, which goes away. You just have to solve for this in terms of b, and you'll get your value, and then we'll have our exponential function. So we'll do 400 divided by 20,000. You know you're going to get a negative answer here with regards to natural log, because you're doing a natural log here of a decimal, a value somewhere less than 1 but greater than 0, and you divide this by 15, and that's your b value, minus 0.2608. So you know this right here is an exponential function which will be curving downwards, minus 0.2608. So let's write our exponential function. Is going to be 20,000, your value of your car initially, times e times minus 0.2608x. Of course, these decimal places will lead to some inaccuracy, but it won't be, you can well say it'll be a negligible inaccuracy. But you see how the procedure was. We use the first set of coordinates to develop the a value, then we use the second set of coordinates to develop the b value, and then we combine everything into our final expression. Both of these equations are good. So that right there is our first question done. We had to develop the equations. Now we're done with our equations, and they're both good. Now for our second question. Our second question will have two parts. Put these equations into work. The first one is find the value of a car at time equals 7 years, and the second one is at what year is the value of that car $10,000. Well, if you look here at the linear equation, and we're doing here the answers for question A, the linear, and then we'll do the exponential. All you have to do is basically plug the value 7 here because time is represented by x in the places of that, and see what your y value is. Let's look at the linear equation. You have 1306.6666. This is the minus value times 7, your x value, plus 20,000, and you get a value over here of 10,853, and that'll be a value coming out of your linear equation, 10,853.33. Now do the same exercise here, but with regards to the exponential. You have a 0.2608, it's a negative exponent, multiply that by 7 because here time is equal to 7. You applied with the exponential base and multiplied by 20,000, and we get a value here of 3,222. And let's see what how it compares. Based on the linear model, if you were to depreciate your car based on the linear, where you do an equal amount each year, because a linear line has a slope which does not change, whereas an exponential function has a slope which changes exponentially, the value of your car is pretty high at time t 7 years. But after 7 years, from 20,000, your value of your car is depreciated so much that you're at 3,000, relatively at 3,000. And that right there, it could be a good thing or it could be a bad thing. If you're trying to sell your car, the value of your car would sell for this if people were going by this model. But if you were trying to sell your car at 7 years and they're going by this, you'll get more money for your car. Anyhow, question A is done. Let's look at question B over here, and we're looking at everything here with regards to both linear and exponential models. Now we're saying here at what time is the value of your car 10,000. Here you're solving for the x value, and you have to put the 10,000 here in places of y. So let's look at the linear equation. We have a 10,000 coming here. In terms of y, we minus it, y-intercept 20,000, and then we divide that by the slope 1306.6666, and you know it's a minus slope. We get here 7.65. So based on the linear model, after 7.65 years, your car is worth 10,000. Okay, it makes sense. Now let's look at the exponential model. At what time is the value of your car 10,000? Well, 10,000 is coming right here in places of y. We have 10,000. We'll divide that by our coefficient value a, which is 20,000. We're doing a natural log of this because we're going to bring that exponent will come down as a coefficient, bringing in the natural log. So that we have that. We'll divide that by minus 0.2608, and we'll get the value here in terms of x, the time 2.657. 2.657 years. Remember here for this b right here, I had a 10,000 over here, and then I have 20,000. I'm multiplying with this 0.2608 minus x. You're bringing this value over here, we have a 1 over 2, and then you're doing the natural log. All of this divides with itself to give you a 1 over 2. And then you have a 0.2608 x natural log e. Hence, that's exactly how this value came out. Anyhow, but look at this. Look at the stark difference between the two. After 7.65 years, your car, based on the linear model, still is worth half of its entire value. But after less than 3 years, your car has depreciated or lost half of its value. And you can see how quickly, based on this exponential model, the value of your car decreases. Now the question here is, it doesn't have to be anything more than a rhetorical question. The question here is, which of these is a better model? Well, if you're trying to buy a car, for you the exponential model might be better because, and you're interested in buying a used car. If you're interested in a used car as a buyer, then this model is good because the person has to sell it to you for less, because as you saw, the value of the car went down pretty quickly. But if you're a seller, you want to go with this because this retains the value of your car longer. The linear model retains the value of your car longer, and you have a higher value of your car for a longer period of time. So it all depends on whether you're a person buying a car, a used car especially, or a person selling a used car. With regards to that, then you know there's a good difference as to what you want to take. But anyhow, this video has been completed. That's about all I wanted to develop for you and express for you here in this specific video. Thank you for watching. Have a nice day.